start. Welcome everyone. This is the third day of SQL workshop. Thanks for joining in. We're going to have a special guest today, Dr. Malika from MIT. And she's currently a technical staff and member at MIT Lincoln Laboratory in the Quantum Information and Integrated Nanosystems group, working on quantum computing with superconducting qubits. Dr. Malika received her PhD from Princeton University, where she worked with Professor Ali Yazani. During that time, she conducted experiments measuring electronic behavior with atomic scale resolution using a scanning tunneling microscope operating at millikelvin temperatures and high magnetic fields. Dr. Malika then moved to MIT as a Pappalardo Fellow, working on emergent phenomena and symmetry breaking in two-dimensional quantum material. At Lincoln Lab, her research focuses on the understanding and improving the important performance of fluxonium and other novel circuits for use in superconducting quantum processors. And we're so happy to have you here. And it's all yours, and we would like to hear your speech. Thank you.
Yeah, thank you so much for the introduction, and thank you for having me here to give this talk. I'm excited that this program is underway, and it seems like you have a very nice lineup of talks over the entire course of the week. So I hope to add to how you think about superconducting qubits and specifically the design of superconducting qubits. And so I'm going to talk about a specific type of dephasing mechanism in fluxonium as like kind of the central portion of my talk, but I really want that to seed a conversation about details that you have to consider when designing superconducting qubits. And I just want to find my laser pointer for this. Can you see my mouse at least? Let's see.
Not
Okay.
now. Oh yeah, it's visible now.
Okay, I just want a laser pointer, but I can't seem to find that. Okay, so I guess I'll just point with my mouse and hopefully it will be clear what I'm talking about. Yeah, and so I wanted to say our work on this dephasing in fluxonium was recently just published in PRX Quantum, so you can either check out the published version or the archive version as well. And I wanted to start by just acknowledging my entire team. So this work was done at MIT Lincoln Laboratory. We have a big group working on superconducting qubits. We also collaborate with the MIT Engineering Quantum Systems Group on MIT campus. And the work that I'm primarily going to talk about was done very closely with all these co-authors. In particular, I want to highlight Thomas Hazard and Kyle Cerniak on the experimental side, and then Augustine de Paulo, who helped us with some of the theory. So to give you a brief outline of my talk, I'm going to start by just kind of really framing this question of understanding noise in different qubit systems, and specifically focused on superconducting qubits, and highlight this metric of coherence that we'll use right now to try to define essentially like one of the metrics that we can use to benchmark superconducting qubits and their performance here. And then I'll give a brief introduction into the fluxonium qubit and specifically the Josephson junction arrays that we use as one component of these qubits, because that leads us then to the central question of how does having these Josephson junction arrays function as really large superinductors? How does that potentially give rise to new error mechanisms, and how can we mitigate for that? And so I'll talk about dephasing that comes from a process known as coherent quantum phase slips, and I'll explain what that is, and then show you our systematic study of this noise mechanism, how we design the experiment, how we can study the parameter scaling of this dephasing over several orders of magnitude, and really try to probe the noise properties in the system. And finally, I want to end with then some outlook, looking at just what kind of different trade-offs do you have within the parameter space available when thinking about qubit designs. So to start, let's even talk about what is a qubit, and then what makes up an ideal physical qubit architecture that we can talk about. So a qubit is a quantum bit, and there we just want to think about a quantum mechanical two-level system. So instead of just a classical bit where you have 0 and 1, the whole point of a qubit is that you can live anywhere on this block sphere if you represent the state space that way. But essentially, you're in an arbitrary linear superposition of the 0 and 1 state, and that gives you your wave function. So to start off, you want a quantum system where you can make some approximate two-level system to function as your qubit of interest. And then you can ask, okay, how well is my quantum information actually preserved? And so that leads us to this idea of quantum coherence. How isolated is this qubit from the noisy environmental degrees of freedom? And so typically the metrics that we use to measure that are the T1 and T2 times, and I'll talk a little bit more about that on the next slide. But now we don't want the qubit to be so isolated that we can't talk to it. We need to also be able to address these qubits and perform what are called gates. And so we want high fidelity and fast single qubit gates, and then we want to be able to interact, create interactions between qubits and do multi-qubit gate operations. And so there, then the metrics become the gate fidelity and the gate time. And then as you start scaling, then you start thinking about the number of gates to implement some algorithm of interest. And so that brings us to this David Schenzel criteria, which many of you may have heard about, kind of thinking about what are the criteria needed for scalable quantum architectures. And kind of we'll touch on some of these aspects, thinking about long coherence times, but then we also, like I said, we want to look for scalability. We need to be able to address these qubits. We want a universal set of gates, and then high fidelity measurement. Great. So if we think about the coherence time of a qubit, essentially that you can think of it in like a hand wavy terms as how long does the qubit preserve its quantum information, but then what does that really mean? There are two different metrics we can look at. We can look at energy relaxation. So that's if you prepare the qubit in the excited state, how long does it take for the qubit to experience a bit flip and go to its ground state, or vice versa, have some unintended excitation from the ground state up to the excited state. And so that measures this T1 time, the energy relaxation time. And this really, the T1 errors come in when the qubit is coupled to the environment at the qubit frequency. So this omega 0, 1 is the qubit 0 to 1 transition frequency. But now you can also say, now we know we're not just a classical state with only 0 and 1, and so we can be in some arbitrary superposition. So there's also this notion of a dephasing time. So how well is our quantum state, this wave function that's in a superposition of 0 and 1, preserving its phase information of the phase between 0 and 1? And so there you can think about, if you prepare a state on the equator of this block sphere, how much is that wiggling here? And so this occurs when there are fluctuations in the qubit frequency. So the 0-1 transition is fluctuating, will give you dephasing of the state vector, for example, on the equator of the block sphere. And that enters into the T-phi term from dephasing. And T1 and T-phi combined together in this way gives us this T2 coherence time that people talk about as well. So 1 over T2 is equal to 1 over 2 T1 plus 1 over T-phi. And so why do we care about coherence times? This also enters into a gate fidelity argument, and there's a lot of caveats in the specifics of this equation depending on the gate sequence that you're performing, but ultimately gate fidelity is limited by the coherence, or depends on the coherence times of the qubits and the time that it takes for you to perform this gate. And you can think about this if you have to do a sequence of many, many different gates, and each of your gates is very long compared to this coherence time, then the qubit is not actually going to preserve its quantumness throughout the sequence of the set of gates. So that's why we care about coherence. And this is very general to, this idea of coherence is very general to any different type of qubit. And as you all know, there are many different types of qubits that people are currently thinking about, and research is ongoing on all these different types of qubits. And broadly speaking, we can have quantum states that are defined by design. And so on one end here, we have superconducting qubits. You can also have quantum states defined by nature. And so there, for example, would be cold atoms or trapped ions, for example, where it's atoms interacting with light as opposed to some lithographically designed quantum state. And really here, what we care about is not just, oh, what's the coherence time, but it is this balance between coherence time and gate time. So broadly, generally speaking, these trapped ions and trapped atoms, for example, have very long coherence times, but also then consequently to perform gate operations, they're almost so isolated from the environment that the gates themselves can take much longer. Whereas superconducting qubits can host really fast gate times, but also have shorter coherence times. But really, the devil is in the detail of these fine balances to say which architecture do you choose to work on and which architecture is best suited for a specific application of interest. And so my work is focused on superconducting qubits. And in terms of the advantages of superconducting qubits, one is just this lithographic scalability, that we're designing these qubits on wafers and semiconducting chips. So we leverage a lot of the fabrication processes that have been developed for semiconductor and superconducting fab processes. And what that means is we have full control over defining the different circuit geometries and way we want to define the components on our chip. And that allows us to engineer many different types of couplings and really tune the strength of the couplings based on our design itself. And this also offers us huge versatility in the circuit design. And another key aspect of superconducting qubits is we do have a lot of freedom with the hardware implementation of individual circuit components. And so kind of some of the work I'm going to talk about is going to touch on these 2 points here in terms of how do we implement different circuit components. Well, there are also some challenges in terms of the calibration that's needed to tune up a superconducting qubit. These material processing can add more disorder that can then affect coherence. And so coherence is really one of the metrics that people try to improve upon in order to get higher performing qubits. So if we think about what are the components that we need for a superconducting circuit, it's basically your standard electrical components. So there are no resistors because we're talking about superconductors, but we can have capacitors, and primarily we define these capacitors just as coplanar structures. So you can see here, this is some metal, there's some gap, and then there's another metal. And so that gives us this coplanar capacitor type of structure, which we can make very, very high quality with high quality materials, but they tend to be pretty large physically. And here, this effective dielectric is just based on the dielectric of the substrate that you choose. Then we can also have inductors, and we primarily use these inductors for resonators. And you can think about there just having a meandering wire, or in this case here, it's a spiral resonator. And then the geometry of your design and then the material sets your inductance value. And then finally, what's special for superconducting circuits is that we also have these Josephson junctions, which essentially acts like a nonlinear inductor. But a Josephson junction is just a sandwich of a superconductor, insulator, and then a superconductor. And typically, like right here in this SEM image, right here, this blue spot is where the junction is actually formed. And this is formed with an aluminum oxide, aluminum shadow evaporation process. But you basically deposit aluminum, which is your superconductor, oxidize some portion of it, and then have a small overlap on top to give you this Josephson junction. And you'll see where that comes into what we think about for superconducting circuits as well. But these are the three different components we have for superconducting circuits, and you can combine them any which way you want to create a circuit and then quantize it and figure out whether it would make a good qubit for your need, just for your needs. And so basically you connect these components up from the circuit, you can derive the Hamiltonian and then take it from there. And so what do we want to think about when we think about these circuits? So I'm going to go to a simple circuit, which is just an LC oscillator. And so it just acts as a harmonic oscillator. You can think of this as a resonator. And essentially here, if you solve the equations of motion, you can see that the energy just sloshes back and forth between the magnetic field in the inductor and the electric field in the capacitor. Now, quantum mechanically, when you quantize this Hamiltonian, what that means is it essentially, instead of saying you can have states at any energy, the energy spectrum becomes quantized. And so you have these discrete energy levels separated by a resonance frequency, h bar omega r, that's just defined by L and C. And in a harmonic oscillator, the energy spacing between all your levels is the same. So what a transmon is essentially, instead of an inductance, a linear inductor, we add a Josephson junction in parallel with the capacitor. And this adds some nonlinearity that makes the energy level spacing unequal. And so the 0, 1 energy spacing is different from 1, 2, and so on and so forth. And what that means is now we can really make this into our qubit, where we think about 0 and 1. And because these energy spacings are now different, if we want to drive a transition between 0 and 1, for example, we know we're not going to drive a transition between 1 and 2, because now the energies are different. And so within the landscape of superconducting qubits, you can have many different ways in which you connect up these circuits. And so historically, people have focused on flux qubits, which have a circuit diagram that looks like this, or the transmon, which is this Josephson junction in parallel with a capacitor. And both these circuits, depending on what regime you choose for the parameters, have different sensitivities to either charge noise or flux noise, which are the two primary ways in which you control these superconducting circuits. And so over the years, people have tried to focus on understanding the dependence of these different noise parameters on the Hamiltonian, different noise channels on the Hamiltonian parameters. And you can see that in this, like over the years, if we look at coherence over time, qubit design has continued to improve both in terms of material processing and the circuit design itself to give us improved coherence times. And so today what I'm going to talk about is this fluxonium qubit, which really tries to take the best of both worlds and combine aspects of the transmon and the flux qubit to make a qubit, which is essentially a capacitor, a Josephson junction, and an inductor in parallel. So it's one of your simpler circuits to realize in terms of just a single node circuit. And so it lives here in terms of looking at, as you go higher up in EJ over EC on this axis here, you become less charge sensitive. And compared to the flux qubit, for example, a fluxonium, you can operate it at specific working points so that it's not as flux sensitive. So this is what the Hamiltonian of the fluxonium qubit looks like. Essentially, each of these circuit elements here just has an energy associated with it, the EJ, EC, and EL terms. And here you have the superconducting loop between the Josephson junction and the inductor here. And what that means is by changing the external flux, you can just thread a magnetic field through there. You can tune the potential energy of the circuit. And so as you see, two different values of external flux. This black line is the potential energy. You can change that. And then consequently, the wave functions and energy levels also change. And what that means is you can see, for example, if we calculate the qubit frequency as a function of flux, as we tune flux, the 0-1 transition frequency for the qubit can change from like a few hundred megahertz up to several gigahertz. So we typically operate at the half flux sweet spot, but you can essentially operate this fluxonium anywhere over this flux range and get a very large frequency range of operation. And recent experiments have shown a lot of promise on fluxonium. They've been shown to have very long coherence times, over a millisecond, and very high single qubit and 2-qubit gate fidelities as well. So what we set out to do was look at noise mechanisms that emerge from a specific implementation of this fluxonium circuit. So really, in a fluxonium circuit, although the circuit diagram I drew was just capacitor, Josephson junction, and inductor, in reality, when we make a fluxonium, we realize this inductor by creating a series of Josephson junctions. And so we have about 100 different Josephson junctions connected in series, which form our Josephson junction array. And just right off the bat to highlight here, we can use the Josephson junction in two different ways in this circuit, both to make a small junction here, which acts like a Josephson junction, but here when we have many Josephson junctions in series and we choose the parameters as such, basically what this means is we can approximate the series of Josephson junctions, the JJ array, which I will sometimes write as JJA, just as a linear inductor. And that works out if you just think about the phase drop across from this node to this node here across the small junction. If that's equally distributed over n array number of junctions, say 100 junctions, then you can approximately linearize this this term in the Hamiltonian here and just get a term that looks like an inductive energy. And so now the question we set out to ask was then, how does having so many junctions affect coherence? And there's something specific to Josephson junctions, which is that phase slips in the Josephson junctions can cause dephasing. And so we really wanted to understand noise mechanisms that can arise by realizing this inductor as a series of Josephson junctions. And this was first studied back in 2012 by Vlad Manoucharian in this paper, which was titled Evidence for Coherent Quantum Phase Slips Across a Josephson Junction Array. And so what our goal in this experiment was to perform a systematic study of this CQPS dephasing and try to understand how it scales with the JJ array parameters and probe the noise power spectrum that emerges here. And really, like I said in the beginning, we asked these questions with an eye towards asking what limits does this put on JJ array design and qubits that use these Josephson junction arrays. So to start off, we have to understand and think about phase slips in a Josephson junction. So we have this Josephson junction, which is a superconductor, insulator, and superconductor. And a phase slip is basically if you consider the phase drop across this element here, this entire component from one side of the superconductor to the other, the superconductivity can allow for discontinuities in the phase as long as the total phase difference is kept the same. So basically this black line here or this red line here with a phase slip looks the same from any observable that you would measure to first order. And so really it's these discontinuous 2 pi phase differences across the Josephson junction. And this can be thought of as a dual to Cooper pair tunneling. So instead of a Cooper pair going from one side of the superconductor to the other, here you can think about a fluxon tunneling from one side to the other of this Josephson junction. And there's some really nice math that works out due to this duality. But for the purposes of our talk here, all you want to think about is that we can have these phase slips that they can occur at any Josephson junction. The rate at which these phase slips occur depends on the parameters of the Josephson junction. So the Josephson junction impedance, that's defined by the EJ and the EC, so the Josephson energy and charging energy for a junction. And in our fluxonium picture, for example, this small junction here has a very large impedance, and so a very large phase slip rate, whereas these array junctions have a much smaller phase slip rate. And so what that means is there are certain phase slip trajectories, or if you want to think about fluxon trajectories, that modify this original fluxonium Hamiltonian equation that I showed you. And so the kinds of trajectories that affect that are these kind of, what I would say is this fluxon trajectory, for example, where we think about a fluxon tunneling in through the small junction, but out through one of the array junctions here. And these kind of fluxon tunneling trajectories are very sensitive to the offset charges at the superconducting islands within the JJ array. And this is basically an Aronoff-Kasher phase, analogous to the Aronoff-Bohm phase, where an electron feels a magnetic potential and picks up this geometric phase here. In this case, it's this fluxon tunneling picks up, so here we have this epsilon PS, which is the phase slip rate, and then the fluxon tunneling picks up this geometric phase that depends on the charges at all of these superconducting islands here. And now we can have a coherent addition of these different geometric phase factors, which just arise from interference due to multiple different fluxon trajectories which could occur. And what this means is this adds a perturbative correction that comes from this phase slip energy and adds this perturbative correction to our original fluxonium Hamiltonian that we were talking about. But all of this so far wouldn't cause any dephasing as such. It would just shift the qubit frequency that we measure because it's a coherent process. But where the dephasing comes in is when we start thinking about the fact that we can have charge noise, and all of the charges on these different superconducting islands can fluctuate. And so if these fluctuate, these NG terms, for example, then our phase slip energy, this net perturbative correction, also fluctuates and causes fluctuations in the qubit frequency, which then if you think back to one of the first slides I showed of that Bloch sphere and that wave, your state vector wiggling around on the equator, that's what gives us this qubit dephasing here. And so there is a whole theory we can go in to understand and extract a theoretical expected rate for this dephasing. So this is gamma phi from CQPS. So gamma is 1 over T2, for example. So this is the dephasing rate that depends on the number of junctions we have in the array, the CQPS energy perturbative correction term to the Hamiltonian, and then there's some other structure factor here that has to do with the matrix elements and states coupling due to phase slips as well. But really what I want to highlight is if we say, so this black dashed line, for example, is the bare qubit frequency for a fluxonium right around half flux. And then if we add this CQPS, coherent quantum phase slip process, for array junctions that have an impedance of either 0.09 or 0.10, you can see that that would then give fluctuations in the qubit frequency, and that this qubit frequency, how much it fluctuates from its mean, is very, very sensitive, exponentially so, to this impedance of the junction arrays. And so that's really the takeaway here, is that it's highly sensitive to this, the impedance of these junctions. And so that's what we then set out to study in our experiment, is exactly this particular theoretical equation here, and the scaling of ECQPS to the impedance of the array junctions. So in our experiment, we had a single chip. So here's a 5 by 5 millimeter chip where we had 6 fluxonium qubits that were designed as such. Here's this fluxonium in the middle. We couple it to a readout resonator so we can read out the state of the qubit. We have a charge drive line through which we perform qubit spectroscopy, and we have a flux drive line through which we can tune the flux in the loop and change the flux of the qubit. And so zooming in here, this is our small junction, and this is the array of many, many Josephson junctions. And you can see this junction, this Josephson junction here, is really small compared to these array junctions. And so when we think about the experimental design and try to understand what is the impedance of the different Josephson junctions we have in our fabricated chip, we designed the experiment to have a fixed Hamiltonian, so nominally keep the Josephson energy, charging energy, and inductive energy the same, but we will vary the phase slip rate from the junctions in the array. And so what does that mean? Is that in our design, what we specifically choose to change is we change the length of these array junctions, and the width is nominally fixed based on our fabrication process. So we changed this length from 1.85 microns up to 3 microns. And these are very, like, fabrication-wise, very easy to access parameters for the length that we're tuning. And then in order to keep the inductive energy the same, we have to also change the number of junctions that we have in the array, just consequently based on this inductance, based on this length number. And so that allows us to tune the impedance of the array junctions. And so up here on qubit 1, for example, we have a very high junction impedance, and so expect a large phase slip rate. And then we tune down by about a factor of 2 in impedance. And you can see we end up with orders of magnitude smaller expected phase slip rate here for our junction. And so really what goes into calculating these numbers is there's some parameters that are set by fabrication processes, like our critical current density or the specific capacitance, and some which are design parameters. And we can walk through the math in more detail if there's interest, but basically then the design parameters consist of the length, the width, so the junction area is really the parameter that you would probably think about, and then the number of junctions that we have. And so we design our experiment as such with our 6 qubits, and when we measure just qubit spectroscopy as a function of external flux, we can see that our 6 qubits all show relatively similar spectra. And so they were all designed with Hamiltonian parameters that are fairly close to one another. But now if we go in and measure the dephasing time, and so this is T phi Ramsey for these 6 qubits, you can see that we see very, very different behaviors. And so this is our real data, the dots, and then the lines are theory lines on top. But you can see that, first of all, on this scale here, the y-axis is a log scale, and the dephasing times of these qubits vary over several orders of magnitude. And you can see that the shape changes as well if we compare, for example, this yellow data set to this blue data set here. And so the first takeaway is that just trying to tune and design a qubit with a particular spectrum in mind, or a particular qubit frequency, is not the only parameter to consider, because identical spectra or nearly identical spectra do not give the same kind of dephasing rates. And then when we went and tried to understand this in more detail, these qubits down here, they're really limited by this coherent quantum phase-slip dephasing process. Whereas this qubit 6, you can see its shape looks very different, and it shows a peak in T phi right at half flux. And this is exactly what we would expect if this qubit dephasing time is limited not by the CQPS mechanism, but by flux noise. And this half flux is a flux noise sweet spot where you can see in the spectrum, the qubit frequency doesn't change with flux. It has a zero derivative right here at its minimum. And so you would expect the flux noise limitation to diverge. And so now we can also look at this in more detail and really see that our CQPS theory here, if we plot the expected or the measured dephasing rate versus the theoretically calculated CQPS dephasing time, you can see that these 5 qubits here line up really well, and there's one free parameter that goes into fitting this data, and that's the specific capacitance for our fab process. And so we fit for the CQPS just a single free parameter across all these 6 qubits and extract these theory curves plotted here and show that these 5 qubits scale very well with our expected CQPS dephasing rate. And this qubit here had such a low expected dephasing rate from CQPS that it's limited by a mechanism that's not the CQPS dephasing. And so that's why it falls off of this line here. And so really the 2 different noise mechanisms that we have to take into account when plotting these lines is the CQPS dephasing and flux noise dephasing in order to also be able to capture this kind of divergence at half flux that we see for qubit 6. And so then we can also look at dephasing over the entire flux range and compare the 2 limiting case qubits that we were looking at, that yellow qubit and the blue qubit. And we see that our theoretical calculations and the 2 functional forms that or 2 noise mechanisms that we can that we take into account do actually match our data over this entire flux range. And there are some details that I could talk about in terms of the shapes of these different curves, but maybe in the interest of time, because I do want to leave time for questions, all I will say is that we have a complete understanding of the difference in shapes and really understanding the relative contributions from CQPS dephasing and flux noise across all these 6 different qubits here. And we also, as we were looking at this coherent quantum phase-slip dephasing, also studied the flux noise dephasing for all our qubits in greater detail as well. But now the thing I wanted to get to was beyond just measuring this dephasing time and looking at those 6 different qubits and comparing them, we were also able to directly measure the noise power spectral density for these 2 different mechanisms here. So we look at qubit 1 that's limited by coherent quantum phase slips and qubit 6 that's limited by flux noise. And so the type of data I'm showing here is just repeated Ramsey experiments. And by doing these Ramsey measurements, we can essentially extract the noise on the qubit frequency. And so if we plot, so basically one of these Ramsey measurements gives us a very accurate measure of what the qubit frequency is. And then if we repeat this measurement 1,000 times, what that means is we can directly measure qubit frequency fluctuations as a function of lab time. So here is the frequency fluctuations around its mean over time. And then if we take the Fourier transform of this basically and extract a noise power spectral density, we can see that these 2 different data sets show very different functional forms for their noise power spectrum. And in fact, if we go in and fit this data, we see that the flux noise limited qubit shows a 1/f noise power spectral density, and we can also extract the flux noise amplitude, which matches and corroborates other independent measures of the flux noise amplitude as well. And this 1/f type of noise power spectrum is very much what's expected for a flux noise type of behavior. And in contrast, the CQPS limited device shows something that looks essentially like white noise or constant at over this sampling frequency range. And then we were able to think about and try to understand some of the microscopics of what could be a plausible explanation for what's giving rise to this type of noise power spectrum that we're seeing for the CQPS limited qubits. And so here it really went into thinking about the microscopics of what this Josephson junction array looks like. And if we have these many different superconductors here, if we think about charges fluctuating, or charges in this case are these quasi-particles that can hop to the left or the right, we were able to create a microscopic simulation that also ultimately gives a noise power spectrum that looks somewhat like a Lorentzian that's constant at low sampling frequencies and then rolls off. And so the data that I was showing on the previous slide that we measured was really in this green box, like that frequency range. So this is a plausible microscopic explanation of what's happening here. And so we do know it's somehow related to charge fluctuations in the Josephson junction array. And there is more we could try to understand with the details of these simulations as well. And then finally, the takeaway here is that when considering this CQPS dephasing, we had one qubit which was not limited by this mechanism. And so we did some extensive simulations and studies to try to understand how best to pick our circuit parameters so that we can design around the CQPS dephasing. And so basically the workflow consists of starting with the Hamiltonian of interest and then checking that all the different parameters that we have in terms of the inductive energy, the critical current density, the area of the junctions, and the number of junctions are chosen so that CQPS is not dephasing, is not the limiting factor. And so, for example, basically to just say, across a wide range of inductive energies and area, we can choose the area of the junctions in the array such that CQPS, we can always be in a regime where CQPS is expected to limit us to a coherence time of 1 second or above. And that's what we kind of show and break out in plots in different ways here. And so finally, just to end and say in general, when thinking about engineering qubits with longer lifetime, the equation to think about comes from Fermi's golden rule that limits T1 and depends on both the noise spectral density of the environment and the operator that's coupling the qubit to the environment. And so you can think about either improving the environment itself, which I would call some extrinsic type of environment engineering. And this involves thinking about different amorphous dielectrics, both at different interfaces like substrate to vacuum or within the junction itself, and improving the disorder there, thinking about other types of noise sources and mitigating those. And maybe just briefly to say, we're also trying to understand the performance of fluxonium in this manner, looking at T1 of many different fluxoniums over its entire frequency range with a goal to try to characterize the noise environment, both in terms of broad trends of T1 and sharp dropouts that may be coming from lossy two-level systems, and then improve on our fab processes in this way. And then finally, also, if we think about engineering different qubits with different Hamiltonians to minimize this coupling between the 0 and 1 states through some operator. And so that leads us to this idea of protected qubits, where people are considering all kinds of circuits with multi-node circuits with many different inductors, Josephson junctions, capacitors. The whole goal being here to try to minimize this portion of the equation that goes into calculating the decoherence. And so we're working on something like this as well with multi-node circuits that are kind of a step beyond fluxonium, looking in this case at fluxonium molecule. But in the interest of time, I think I'll just come to the end and say, really to tie it all back together, I hope I've left you with some sense of how the circuit components for a superconducting qubit themselves have a lot of flexibility, and we can use the Josephson junction itself as well to play different roles in the circuit depending on where we put it and what parameters we choose for the Josephson junctions. And then the one aspect to think about are the phase slips at the Josephson junction and how that affects the circuit properties. And so for this coherent quantum phase slip dephasing experiment that I talked about, we really were able to verify the scaling of CQPS dephasing with the JJ array parameters and characterize the noise power spectrum as well. And then in terms of thinking about designing around the CQPS dephasing, there are many different trade-offs because it's a multi-dimensional parameter space, but there are ways to sort of have some design best practices to not be limited by it. And these ideas are broadly applicable to many of those protected qubit circuits that I showed, which all use these JJ arrays as inductors in there. And so finally, just when thinking about designing optimal qubits, it's important to both consider the noise environment of the qubit and the Hamiltonian matrix elements as well. And so yeah, the devil is really in the details, but it's really possible with these superconducting circuits to work through those details, both experimentally and theoretically, as you go to design your qubits. And so with that, I'd like to open it up for questions.
Really, thank you for this super cool speech and lecture. We've loved it. So many questions from attendees, starting from Tanwir Ahmed. Could you please answer how is the coupling G calculation of fluxonium qubits with its readout resonators differs from that of a transmon?
Yeah, so it is a good question. Basically you have to do the full calculation. Like you cannot make as many approximations in a transmon. For example, you just say, oh, it's some G, and then you look at the resonator, the difference in frequencies between the resonator and the qubit. And that's all true in fluxonium as well, but you have to think about the fact that there are matrix elements of the fluxonium that change. And so you would just do the full Jaynes-Cummings Hamiltonian calculation, for example.
Thanks for your great answer. Moving to the next question, could you please tell us that what makes fluxonium have a large coherence time?
Yeah, I think so fluxonium has different properties that are of interest depending on the type of application, but in terms of the long coherence time, it has, so one of the dominant loss mechanisms that people have identified in superconducting qubits is this dielectric capacitive loss. And so for transmons, for example, there's a simple way to think about the quality factor of a transmon. Q is about equal to omega times T1. So if you have a higher frequency transmon, you're going to end up with a lower T1 for the same quality factor set by whatever loss mechanism you're thinking about, but often for superconducting qubits, it's dielectric loss. For fluxonium, this equation also has some matrix elements that depend on, again, like a full calculation of Fermi's golden rule. And so it's not as simple of a equation, just like omega times T1 equals Q. But what that means is that by looking at the matrix elements, like a low frequency fluxonium can have much higher T1 compared to a like comparatively similar transmon with the same qubit frequency, for example.
Thank you. I hope Ahmad could get his answer. And moving to the next question, uh, why Hamiltonian influxonium is not required to be expressed in second quantization form?
Oh, you could write it in second quantization form. This was the like simplest way, I would say, of writing it with like making all the operators, I guess the variables, phase variables as operators and imposing some conjugation, or whatever
Mm-hmm.
it's called, the canonical conjugation um
Yeah.
aspect of quantum mechanics on it. But you can then break up the phase operator as some like A plus A dagger and A minus A dagger and write it in second quantization form.
Yeah. And when you are approximating many Josephson junction arrays as linear inductor, how good is the approximation exactly?
That's actually, that is a very good question. And it's, I would say to first order, it is a good approximation, and there are a lot of open questions, some of which we are still trying to think about and work on and understand. And so, I could just go back actually and show you. So the first order thing, the reason why it's a good approximation is if you say you have 100 junctions, you're just doing a small angle approximation of a cosine. And so that two first order is not a terrible. So if you say you have n Josephson junctions in the array with an EJA and they each have an energy that's cosine and now phi over n, because if I say the phase drop across the small junction is phi, and now the phase drop across a single Josephson junction in the array is 1 over n of that. And so, yeah, you could say, okay, there's some disorder in these junctions, and so this phase will, then you pick from some distribution and you can go through all of those calculations. But to first order, if you say you have 100 junctions and then your phase drop is something divided by 100, it's not a very bad approximation. And so in terms of like first order spectroscopy data, for example, for our qubit, this equation with just having the approximation be an inductive energy that just has a phi squared term fits pretty well.
Mm-hmm. And really, thank you for your answer. Moving for a question from Zuhair. Fluxoniums require a larger area compared to transmon qubits. Do you think we could still use fluxoniums for large quantum computers, given that area seems to be at a premium? Additionally, if the junction is shunted, does that leave the qubit unusable?
So the qubit is typically shunted. Let me answer that question first. And so here, this is our fluxonium with the small junction and the JJ array. And then these two squares here are our shunt capacitance. So we do put in that shunt capacitance as well, even for fluxonium, for similar reasons as you do for a transmon. And I would say the footprint of a fluxonium is not that much bigger than a transmon. And right now with scaling superconducting qubits, yes, the footprint of a qubit is one concern, but there are also like perhaps higher, like more pressing concerns in terms of just being able to get all the control lines routed through to the qubits. For example, even if you make a 5 by 5 grid of qubits, how do you start controlling and addressing the qubits in the center of the grid in this type of planar geometry structure, right? Like then you're saying, oh, suddenly I have some qubit in the center of the chip and I need to get a line in. And so people are working on workarounds around that. But I think people are also trying to scale up fluxonium qubits to make larger quantum processors as well. And this is one of the open questions in the field of superconducting qubits is like transmons are the most developed qubit that have been worked on for the longest time. And so they've really been pushing the forefront of making these scalable devices, but it's not clear that that's necessarily the answer. And so people are also still interested in looking at Fluxonium and other qubits as well at different stages of scalability.
And moving to the next question, for the design parameters, the equation looks analytical. We're estimating these design parameters using exact or numerical techniques to decrease facelift error further. Could you comment on these equations at macroscopic level?
Yeah, so I guess I would say these equations are very, very standard when thinking about how to design a superconducting qubit. It's just saying, okay, what's my capacitance? And you're right, these are analytical in the sense of these are the simplest ways to think about, okay, what's the capacitance of just two pieces, like a Josephson junction with, for example, you have a piece of metal with a certain length and a certain width. What's its capacitance? Given that capacitance, which has one parameter, which is capacitance per unit area times area. And then given this capacitance, what's the energy? And then that's E squared over 2C. There is also a whole side of superconducting qubit design, which is, okay, take this layout of these particular like parts of like metal capacitor pad here and then ground plane here and run it through a full E&M simulation to figure out what's the actual calculated capacitance. And so that, in some sense, that kind of E&M simulations are computationally intensive, but do give you a more accurate estimate of like capacitance considering all the metal surrounding a particular element of interest, for example. But all of that would just add corrective terms to this kind of calculation. It wouldn't necessarily change. So it may change the quantitative numbers of these facelip rates, but it couldn't be used to minimize facelips completely. Like that needs to come in from the design. And so these kind of equations here give you the first level of intuitive understanding for where facelips could be coming from and how to design around it. But then, yes, you should go back and check your full E&M simulations for these numbers as well.
Really appreciate it. Moving to Jerrison's question, do these different kinds of noise affect the gate depth differently? And if so, how is that?
Do the different kinds of noise affect what?
Gate depth.
Oh, gate depth. Yes, definitely it would affect gate depth. We did not in these experiments really study a like full sequence of, for example, doing randomized benchmarking to calibrate the gates or more complicated like gate set tomography or other mechanisms like that to try to understand how different noise mechanisms affect your gates. But definitely different types of noise mechanisms affect the gates differently. And in particular for understanding errors on gates, people care about whether the noise is Markovian or non-Markovian. And so you can think about this in terms of, does it have some long time effect? And so is it saying doing your gate now and doing your gate like 10 gates later actually look like different gates to the qubit or not? And like, are there just some simple like over rotation, under rotation errors, or is there some longer time transient that needs to be corrected for? So definitely that is another layer to understanding noise mechanisms, is then to say, okay, how do these noise mechanisms affect gate depth?
Really appreciate it. Thank you. Do the noise mechanisms, Fluxonium are much more accurately determined than transmons. So better noise modeling, better mitigation and control compared to transmon.
I wouldn't say that the noise modeling is better than a transmon. All of the equations that we use are generally applicable to any qubit. If you have the Hamiltonian, then you can calculate matrix elements for different states with different operators, like considering flux or charge or different noise mechanisms. And it's all the same equations. It's just understanding the details of how the matrix elements couple to your different noise mechanisms and whether that makes fluxonium, for instance, more or less sensitive than a transmon to a noise mechanism. And I think I also would point out that the anharmonicity of the fluxonium at half flux, for example, is very large, which is different from a transmon. And so that also adds in terms of, it's an added benefit in terms of thinking about leakage to higher states.
And moving to the last but not least question, could you please tell us the phase slip energy looks similar to the nearly non-orthogonal states in photon tunneling of the type bonding model. Can we say that the flux tunneling through each junction picking up the phase?
Yes, exactly. I think that is exactly a very nice way to put it. You're right. It's exactly like a tight binding model that you can think of coming from this flux tunneling that also picks up a phase. Yeah, and that's this geometric phase. So exactly.
Hmm. We really thank you, Dr. Malika from MIT Lincoln Laboratory. We were so happy to have you here. And speaking for myself, since I've been working on fluxoniums, it was super cool lecture. Thank you. And we've learned a lot from you.
Yeah, thank you so much. And I look forward to just staying connected. So I'm happy to be in
Yeah,
touch. Yeah.
sure.
Okay.
I hope so
All
as
the
well.
best.
Thank
Enjoy
you.
the rest of the talks. Thank you for all your
Bye.
questions. They were very, very good questions.
And thanks for your reading lecture today by Dr. Sebastian Bloch. Dr. Bloch earned his PhD in applied physics from Delft University of Technology, completing his PhD at the QTech Institute in 2015. After postdoc work at UC Berkeley and Lawrence Berkeley National Lab, he joined the University of Rochester as assistant professor in 2020. His research focuses on quantum information science, particularly using microwave photons in superconducting circuits and Josephson tunnel junctions to process quantum information in higher dimensional nonlinear oscillators. His work bridges quantum simulation, sensing, and explores key questions in quantum information, high energy physics, and condensed matter. Now we will be presenting the lecture Beyond Binary Quantum Information in Superconducting Circuits, taking the transmon for this spin. Thank you, Dr. Bloch, for being here, and we're all ready to hear your lecture. Thank you. Please go ahead.
Excellent. Thank you. Thank you so much for the very kind invitation and the kind introduction. It's my pleasure to be here and talk on this event. So my goal for today is to try to convince you that quantum information is not just limited to two states. You can encode quantum information in multiple levels if you want to. We will do that in this very deep stretched potential that I have on the right side here. And I will try to do a good job at giving you some introduction to superconducting circuits. Some of this might be a little bit of a repetition of some of the things that you've already seen earlier in this event. I hope that that's not redundant and helpful to see this from a different perspective. And so really the idea is that we make a very deep potential for trapped excitations in a superconducting circuit that we then climb the transmon ladder to look at beyond binary quantum information encodings. And then I'm going to take this for a spin. With which I mean that we're going to interpret this as a large angular momentum spin system, where we can make these beautiful plots of the quantum states of large angular momentum spins. And all of this happens on superconducting circuits, of which you can see a small hint here at the bottom. And it's my goal towards the end to have you understand all of this. Starting with the beginning, though, I'm teaching quantum physics recently, and what I tell students in undergraduate is that there's just two problems that you need to understand if you're learning about quantum physics. And normally I make this an audience participation question, but maybe I invite you to think about the two problems that you think you would need to understand to solve really many problems in quantum physics. And my answer to the students is you need to understand a two-level system, spin half, and an infinite dimensional system, an harmonic oscillator. They are characterized by, in the case of a spin, being highly nonlinear because there's no excited states, and you can visualize a spin half state on the Bloch sphere here. And then on the other end, the harmonic oscillator has infinite dimensions. It is linear in the sense that the energy needed to go from 0 to 1 and 1 to 2 is all the same. And you can represent the state of a quantum harmonic oscillator in this infinite dimensional phase space using either your canonical variables expressed in position momentum or alpha or I and Q, depending on how you prefer to think about this. For the sake of this talk, I want to introduce a third flavor that combines, in my opinion, very interesting aspects of both of these, and that is a large angular momentum spin. This is something that is nonlinear with a dimension higher than 2, but less than infinity. Because of this high nonlinearity, you can still control it really well, but because you have higher dimensions, it gives you some of the freedom to do things that you could not do with just a single qubit. And today, I will show you how we implement such a large angular momentum spin, or like an effective large angular momentum spin in superconducting circuits. Why are we interested in making more complex and different quantum systems? Starting very briefly at the beginning, I would say the dream of our field of a quantum engineer is to create very large-scale quantum systems and essentially have individual control over these quantum systems. Right? You could think of your computers or a laser or any other technology already as a very large quantum system that we control. But the difference is that you don't control the individual quantized excitations. Now, why is this interesting? This idea was maybe first advocated by Richard Feynman in the 80s, stating that if you want to simulate phenomena in nature, he realized that they have or can have exponential complexity, which he means that if you have an n spin half or an n quantum bit state, at any given time, you need 2 to the power n complex numbers to describe that state. And that leads to a type of exponential complexity that is very hard to grasp in general with classical methods or analytical methods. And so having a machine that can control such a system might give us answers in, for instance, solid state physics or in chemistry or in fundamental physics, because fundamentally we know that nature is quantum mechanical. And so if there are important quantum mechanical features that are at play, then likely you will need a quantum computer or a quantum simulator to access them, just because of this exponential complexity. About a decade later, this idea of quantum computing was first introduced by the introduction of two algorithms, Shor's algorithm and Grover's algorithm. And those works really drove the field of quantum information processing. It drove many experimentalists to try and go into their labs and try to control individual quantum systems, because now there was a clear motivation for doing so, in addition to this idea of quantum simulation. Now, I'm not going to give an extensive summary of this field right now, but I just want to show and flash some of the recent experimental breakthroughs that are just an example of the breadth of this field that happened in the past 3 to 4 decades since proposing quantum simulation and quantum computing. Again, this is not an extensive overview, but what this shows is that these breakthroughs are in many different fields. They range from quantum computing or information processing to quantum simulation, and even quantum foundations or learning fundamental things about nature. The breakthroughs are across many different platforms, including superconducting qubits, neutral atoms, MV centers, photons. And then as a final remark, some of these breakthroughs have big claims, and I think there's reason for a lot of excitement. We also have to be very careful in interpreting some of these breakthroughs, So for instance, on the topic of can quantum computers now outperform classical computers, the first claims have been made in 2019, and in the past years, other platforms have also made claims. And here really there's an ongoing debate between the best classical methods and the best quantum methods. In principle, we expect the quantum machines to outperform the classical machines because of this exponential scaling. But really, once an experiment is presented here, you can come up with better classical algorithms. And so currently there's a bit of back and forward here. And I will also state that at this time, we don't really have a good idea whether we will ever be able to make quantum machines that will outperform classical computers at a useful task, or do quantum simulation that is actually useful. But I think that that is really what makes this field really exciting. And I would urge young people listening and tuning in here to be mindful of too big claims and be very critical of what can be done. But also I want to infuse some enthusiasm, because really, if you look at the kind of things that have been done in the lab in terms of like the size of systems that we can control now, it's really quite remarkable. One thing that I think the field realizes is that all of these demonstrations have been done on somewhat noisy quantum machines without a means to correct for errors. And so I think it's generally understood that to really benefit from this exponential complexity in this complex machine, we need some form of error correction. And if I just very briefly review the idea of error correction, maybe in the 90s, 2000s, the first qubits came about in various different platforms. And it was already before realized that they will have some inevitable noise, that if you don't fix it in your experiment, this probably prevents you from doing anything useful. And so the idea is that rather than having a single physical qubit, you need to encode your quantum information in a multitude of physical qubits, and you encode the information redundantly. And then by doing measurements that essentially extract entropy without learning what the quantum state is, you can do error correction. And that was first demonstrated in the early 2000s, 2010s, with a handful of quantum bits in a variety of different platforms. And very recently, I think as recently as last month, the first claims of doing this in a fault-tolerant way. That is to say that the individual physical qubits may have some number of errors, but as long as you make the redundant encoding size of the system bigger, then your error correction code makes your logical error go down. And that was first demonstrated just this year. And just to highlight the advances in this field being really exciting, even though I should note that this is experiments of still encoding a single logical qubit. So we're still quite far away from doing the things that were envisioned in the 80s and 90s in that sense. Another interesting development that goes towards the topic that I want to discuss, and that's the topic that we are looking at, is doing these kind of quantum information experiments, but don't use qubits, but use higher level encodings. And for in the topic of quantum error correction, this was done with bosonic quantum error correction encodings, where the information is not encoded in a single two-level system or a connection of two-level systems, but in a single bosonic state that is controlled through a strongly nonlinear state. And so this is one example of the beauty of going beyond this binary encoding, because now the redundancy can come from a single physical element, a single bosonic mode, and you just use the higher dimensional Hilbert space to get this redundancy. And so there's some error efficiency to this argument. And that inspires our lab to think about these beyond binary encodings. So how do we think about that then? Well, I would say a lot of somewhat conventional quantum information experiments are thinking about connecting qubits, for example, spin-half systems, but they can be any effective two-level system. If you can entangle them and control them individually, then you can turn that unitary control into some universal quantum processor. A universal quantum processor can do any task that you're interested in, be it running a quantum algorithm, doing quantum error correction, doing quantum simulation. And really the challenge to making these systems work, although they depend per platform, is that in general, if you have a large quantum computer base of qubits, you need many entangling gates. And it just so happens that this entangling operation is one of the hardest things to do. And so the idea of encoding rather in qubits in n-level systems where n is larger than 2 is some argument of resource efficiency. So it is shown in theory that you can do more efficient circuit compilation by essentially condensing the quantum information into fewer building blocks that have more degrees of freedom per site. And so you generally need fewer entangling gates to do the same algorithm, and you get a log2d scaling advantage if you use qubits with dimension d rather than qubits. Furthermore, these qubits could be very nice for natural redundancy and error correction. And then also in the topic of analog simulation, while a qubit processor is universal, therefore it could in principle simulate any Hamiltonian. Some Hamiltonians that you want to simulate in nature might not naturally be consisting of two-level systems. And therefore the idea is, why not use a quantum simulator that naturally mimics the system that you want to simulate, for instance, a spin-1 chain or quantum fields. And so all of these are directions that we are pursuing in our lab. But for the purpose of today, we will mostly focus on the question, how can we control and encode a single qubit in a transmon? So for the rest of this talk, my plan is to give a very brief tutorial on quantizing superconducting circuits, focusing on the two basic control elements that we have, the cavity and the transmon. And then from there, I will discuss how we use our transmon and cavity to encode and control beyond binary quantum information. So starting with the idea that you can quantize bosonic modes in superconducting circuits, I usually like to start off with this lumped element representation of an LC circuit consisting of an inductor that has a magnetic field and a capacitor that has an electric field. And then you can find its resonance frequency as 1 over square root of the inductance and the capacitance. If you quantize this circuit, it turns out that you can get a quantum harmonic oscillator that in the end is described by the raising and lowering operators A and A dagger. And it's more convenient to think about the flux through the inductor and the charge on the capacitor. So this is a good model that represents our quantized bosonic modes. I like to think about this in terms of the geometry as well. And so the geometry that we often use is this coplanar waveguide resonator, where we have a center conductor made of some superconductor, in our case it's niobium, on top of a silicon substrate. And then there's an electromagnetic mode between the center conductor and the ground plane on each side, where the electric and magnetic fields have, I mean, it's not as easy to see the connection between the electric and magnetic field in this simplified LC circuit, but there's still an electric and magnetic field that in this case we can quantize, and it lives in this coplanar waveguide. If we then create boundary conditions, so we make this waveguide open on one end and short on the other end, we can get a cavity. And this is data from our lab where we made 8 of those cavities. And we can measure them through a common transmission line where we send in a electromagnetic signal, and then we measure the reflected amplitude here and phase. And you can see that every resonator here has a distinct resonance frequency. And that is essentially because we made it each resonator at slightly different lengths. That's at the resonance frequency. And then we can frequency multiplex, reading out each resonator through a single transmission line here. Right. So that gives us the bosonic mode. We then need some kind of nonlinearity to have these quantum harmonic oscillators, or to introduce the idea of doing quantum information and quantum computing with these bosonic states. And to that end, we introduced the Josephson tunnel junction, which gives us an effective nonlinear inductance. It is represented by this symbol of a cross here. This is a picture of a Josephson junction made by MIT Lincoln Labs that made the samples that we will talk about results in this talk. And essentially they consist of an upper superconductor made of aluminum, layer of aluminum oxide that is insulating here in, not visible, but it would be in this region here. And then a lower layer of aluminum superconductor to complete the junction. two ways in which you can use junctions to make quantum bits, and these were the first two demonstrations of quantized circuits that can encode qubits, are to either encode a flux qubit, where the encoding is in the two logical states are either a loop of superconducting current going clockwise with the flux pointing down, or counterclockwise with the flux pointing up, or using a charge qubit where the encodings are really the amount of charges that live on one end of the capacitor versus the other. And so microscopically, I like to introduce these because they are somewhat intuitive to see how superconducting circuits can encode quantum information in two-state systems this way. In practice, though, it turned out that the flux qubit is very sensitive to flux noise, and the charge qubit is very sensitive to charge noise. And a common circuit that is now used, although we are looking for new and better circuits, is called the Transmon circuit, which is the circuit that we use for most of our QDIT experiments in this talk. It is essentially the same circuit as the charge qubit, but we tune it in a regime where the ratio of energy stored in the junction, EJ, over the energy stored in the capacitor, EC, is very large. And that makes it very insensitive to charge noise, because it you get this cosine potential here that encodes multiple energy levels. On a chip, it looks like this here. This is again a chip from MIT Lincoln Labs, where this big cross here makes up the capacitor with respect to ground. And then in the lower left corner, you can barely make out the junction that is the Josephson junction to complete this Transmon circuit. If you then connect a transmon like this to a resonator, and you can already see the connected resonator on the top right of this picture in the lower right of the slide, you can recreate a circuit cavity QED experiment that essentially maps a cavity transmon to an effective atom into a cavity. You can detune the cavity from the transmon, and then you can do the qubit approximation on the transmon circuit. So you replace the A's and A daggers by Pauli spin matrices. And then you get this canonical dispersive James-Cummings Hamiltonian, where in red you have a quantum harmonic oscillator for the cavity. In blue, you have a effective spin 1/2 for the transmon. And the coupling between them is this dispersive coupling that effectively shifts the frequency of the qubit for every microwave or photon excitation that you put in the cavity, or vice versa. And the spectra of the two individual elements are given here: a harmonic oscillator for the cavity on the left, and a cosine potential encoding non-equally spaced energy levels for qubit or qdit, or the transmon, on the right. Now, while this circuit has been, or this equivalent Hamiltonian has been studied in AMO physics for many years, what is really special about superconducting circuits is that we can make the coupling between them really strong. And the one reason is that the wavelengths, the effective wavelengths here, or the frequencies that we work with, are very low, meaning that the wavelengths are very long, meaning that you don't have to put them really close to get this strong coupling capacitance. And this is a beautiful experiment in 2006, which demonstrated that you can do spectroscopy of the qubit. And then if you do this for a growing number of photons in the cavity, you can resolve the individual quantized states of the field in the cavity with the qubit. And so one way of interpreting this data here is that for increasing photon number n here, it is the qubit that is counting how many photons there are in the cavity, going from left to right here being 0 photons, 1 photon, 2 photons, until you go to higher photon number and the state becomes essentially looking classical. So this is also the nature of the principle that we use to do readout. So we can now do spectroscopy of the cavity. So we now do the opposite. So we now do spectroscopy of a cavity for a given qubit state. We pair the qubit in the ground state and we sweep, similar to the frequency multiplex measurement that I showed earlier. We sweep the frequency of a cavity excitation tone, and we measure its reflected amplitude and phase. And you see this typical response of the cavity. If you do that for the state of the qubit in the excited state, you see that the cavity frequency shifts. and it shifts by an amount chi, that in this case is about 200 kilohertz, that is set by the capacitive coupling between the two. If you were to take a single shot of this experiment and you look at the phase and amplitude response in the IQ plane here, a single point here would correspond to a single measurement. And every time we repeat that measurement, we get a single point in phase space here that represents the state of the reflected field. And you can see that when we prepare the qubit in the ground state, most of these points circle on this lower left quadrant, whereas if we prepare it in the excited state, most of the phase space representing the reflected field will center around the upper right quadrant. And if we draw an imaginary boundary here, we can do single shot readout depending on where we land in measuring this reflected field. And that is a means to do qubit single shot readout. Now, for the purpose of this talk, we want to think about using this circuit to encode higher dimensional quantum information. And I want to contrast what has been done in the past already by plotting the number of encoded levels as a function of nonlinearity. And then a qubit would live here in the bottom right, where we have a very strong nonlinearity measured by the energy difference from going to 0 to 1 and 1 to 2. In many qubit cases, that's about 200 megahertz, but it only has 2 encoded states. Now, in the case of bosonic quantum error correction, or just in general bosonic quantum information, this lives on the top left here, where the nonlinearity of the cavity is very weak, but the number of levels is fairly high. In principle, it can be infinite dimensional. In many of these experiments, they go up to level 10 or level 12 or something like that to do error correction. The challenge, though, is that to do quantum information experiments with bosonic cavities, you need some form of nonlinear control. And that usually comes in by coupling the system to a nonlinear qubit. And so the encoding is nonlinear, but you need some form of nonlinear control to go beyond what can be done classically. One experiment that has moved away from this trend is the Kercat, where the energy levels are somewhat spaced, but they are still within the bandwidth of a single excitation pulse. And essentially, what we are trying to do here is we're trying to move in this direction to this upper right, where we have many encoded transitions, and every transition is separated in frequency such that we can address them individually. In the past, it has been demonstrated with Q-trits and even with Q-quartz, so 4-level systems. And for the purpose of this talk, we want to ask the question, how high can we take this control? So how many levels can we control, and how would we control them within a single transmon? So that concludes this brief tutorial on quantized superconducting circuits. I've introduced this idea that we can have an effective Jaynes-Cummings Hamiltonian or CQED Hamiltonian consisting of a cavity or a resonator and this nonlinear transmon circuit. And what I want to ask now is how many levels can we in principle encode in a transmon? How can we read them out? How can we best control them? And is there a penalty to going to these excited states? Are they more noisy maybe? And then I'll conclude with a little bit of an outlook. So starting with this question, how many levels can we encode in a transmon? The two parameters that we can that we have to our disposal are the energy in the junction and the energy of the capacitance. And if you fix the frequency at which you want to work at, for example, at 5 gigahertz, then the free parameter that you have left is the ratio of EJ over EC. And here I plot the potential and the energy levels as a function of phase and charge for different ratios of EJ over EC. The typical value of transmons in many experiments is an EJ over EC of about 50. And what you can see is that the energy levels as a function of charge become very flat for the first 2 levels, which is good to encode qubits, but then they start to have some dispersion, some variation with charge as you go higher up. And then if you go to even higher EJ over EC, 2 effects are visible. First, you see that the energy levels of the higher excited states become more flat, but also you can see that your potential becomes deeper, essentially fitting in more levels within this given potential. And so that is the regime that we are interested in here. I will note that it's not all good news, because as you increase the ratio of EJ over EC on the x-axis of this graph here, well, you reduce charge dispersion for every level, and the higher level you go here in the light coding here, the higher the EJ over EC you need to get to a certain level of charge dispersion, where charge dispersion is defined as the energy difference between state n and n-1 for one charge state and the other charge state here. So it's the amount of wiggle that you have in these energy transitions. The penalty that you pay is that the anormalicity, or the amount of nonlinearity, or the frequency separation between each transition goes down. And so the system becomes less linear and therefore harder to control. So we set out to design circuits that have different EJ over EC for 6 different transmons. This was done by my 2 PhD students, Ray Parker and Xiahao Wang. For the experts in the audience, these are some of the parameters that we used on this chip, where the main thing that we varied, again, is the ratio of energy in the junction over energy in the capacitor. And that led to an anormalicity ranging from 250 to 120 megahertz. And all of these qubits are operated around 5 gigahertz. This was done in collaboration with MIT Lincoln Labs, the Superconducting Qubit at Lincoln Lab Foundry Squill program, where we can make the designs and they fabricate the circuits. And the data here on the left is an example of an early design where we show that the lifetimes of these transmons that they made for us are working really well, showing the energy relaxation time of the first excited state and the second excited state. All right, so we then will focus for the purpose of this talk on 2 of the QDITs that we made, QDIT 4 and QDIT 5, that have these values here. And then what we wanted to do first is to see how many levels we can fit inside of this high EJ over EC transmon. So this is an example of the measurements that we showed earlier, where we just show the cavity spectroscopy for the first and the second excited state, where the first excited state is just prepared by letting the system relax and then exciting the system with a single resonant pulse, exciting just the 0-1 transition. But now we can increase this experiment, increase the number of excitations by preparing the second excited state and doing cavity spectroscopy. And we see that the cavity shifts even further. And then we can repeat this experiment, preparing the third excited state or the fourth excited state, climbing the transmon potential all the way up to the 10th excited state, and still showing a nice dispersive shift of the cavity, demonstrating here that we can control up to 11 levels if you include the ground state in a transmon of an EJ over EC of roughly 250. And if you would do the math, you would conclude that the number of levels that you expect to be able to control is roughly square root EJ over 2 EC, which in this case is about 11. And so that is consistent with the prediction that we made. So if I take this data and I collapse all of these states, not on the same axis, but I offset the y-axis a little bit, I actually get a plot that looks very similar to the data that I showed all the way in the beginning of this experiment in 2006, where they did qubit spectroscopy to measure the excited states of the cavity. This experiment right here is the exact opposite. It's doing cavity spectroscopy to measure the excited states of the artificial atom, or the qubit, or in this case, the QDIT, the transmon. But the difference is that because we have this very strong nonlinearity, we can individually address every transition, and therefore we can individually prepare excited states. We can prepare all the individual Fock states here. And so encoding our encoding our excited state QDIT in this very strongly nonlinear system has the advantage that we can individually control every level and prepare every Fock state. Whereas in contrast here, the excited states were prepared by sending one coherent pulse to control all the levels, and then you get this coherent state that very much resembles a classical electromagnetic state. So that's the power of this particular approach, that you have this control and you have this high dimensionality. So then moving on, we have shown that we can encode many levels, but how can we read them out? this is an example of a slightly different transmon with slightly higher EGO over EC, where also here we showed that we can control up to 12 states, up to the 11th excited state. But then if you think about what happens if you park your readout tone at a single frequency here, you can only distinguish a finite number of excited states until these higher excited states all look the same from the perspective of the single frequency tone. So really what we need is we need to excite this system with multiple readout tones to get the state discrimination of all of the excited states at once. So here I show the IQ plots that look like readout of the 0, 1, 2, 3 state, the 3, 4, 5, 6 state, and the 6, 7, 8, 9 states. And if we send all of these tones simultaneously to our chip, we measure the reflection, we demodulate every tone at its individual frequency, you can in principle map out all of these excited states. But now there's the problem, which is if you think of this as every tone individually reads out 4 levels, how do you process that data and how do you assign the readout state? Because for instance, what if these 3 tones disagree with each other? What if one of your readout tones concludes that Q dit was in state 2, whereas your second tone concludes that it's in state 3, for instance? How do you decide there? And what we ended up doing, trying to solve this problem in 2 ways. The first was to fit the 6-dimensional problem, because we have 3 tones and every tone gives us an I and a Q. So you can think of this as a 6-dimensional Gaussian problem. We can fit a Gaussian model to this. And doing that, we were able to prepare the 10 excited states and read them out with an average fidelity of 85%. The main limitation, you can kind of see it from this matrix, is if we prepare state n, say state 7, we have some finite probability of reading it out or assigning it to state 6. And that is because of readout decay, T1 decay during readouts. If we do the math here, we would estimate that our limit based on the T1s is about 88%, which corresponds very well to what we measured. And so that's the main limitation here. But this method is actually integrating the signal. So when we send the readout tone to the cavity, we integrate the signal to get the points in IQ space, and it ignores the time-dependent information. And it is shown already for qubits that if you take into account the time dependence, you can kind of catch T1 events and identify them and make a better estimation. And one way to do this is to feed the full time trace into a deep neural net. And when we do this, we get higher fidelity. The penalty that you pay is that it's computationally more complex. So there are improvements that could be made to try to see if you can do this more efficiently. There are known limitations to our experiment as well. We know that we can move to reflection, that we can probably, that we are currently in the undercoupled regime, and by going to the overcoupled regime, either by reducing the losses or increasing the coupling to the cavity, we expect to get higher readout fidelity. And then finally, there's some interesting resonator qubit dynamics, or QDIT dynamics, I should say, that could be understood in the context of what's called readout ionization or transmon ionization. And we're working on understanding the complex dynamics there to both understand the fundamentals and improve readout fidelity of this QDIT. Good. So this shows that we can encode and read out a multi-level transmon. The next question that we asked is, how can we best control this system? And this is where we start to give our spin to the transmon. So introducing this topic of efficient QDIT control, the motivation of doing QDITs was that we said initially when we thought about quantum information processing, the benefit of QDITs is that it moves many non-local gates or entangling gates onto effective local gates. If you do the same computation and you compare the QDIT and QBit case, you need fewer entangling gates in the QDIT case. And so the penalty that you pay is that you need to do more non-entangling gates. You need to do more single QDIT gates. And so it is really key to make this QDIT advantage work, to be really good at controlling individual QDITs. The common approach so far to do this is to do what is called individual Givens rotations, which essentially connect neighboring energy levels by driving them resonantly. And then if you do this sequentially, you can get universal QDIT control. And to do an arbitrary qdit rotation in a d-dimensional Hilbert space, you need about d squared of these given rotations. And visually, you can think of it here. If you do an SU4 rotation, so if you want to control a q-quart, you can decompose an arbitrary q-quart rotation in these given rotations, sequentially addressing transitions. But if you just look at this control scheme, you can already see it's somewhat inefficient because at any given time, a pulse is only hitting a single transition and the rest of Hilbert space is sitting idle. And so the idea that we had is, can we come up with a more efficient way of controlling this large dimensional Hilbert space? And this is what my student Liz Champion has been working on. And the solution that she found was to think of our cavity transmon system as an effective large angular momentum spin that is coupled to a cavity. And the first realization was that a Kerr nonlinear resonator that can approximate our transmon Hamiltonian, the spectrum of that can be mapped directly onto a large angular momentum spin in a magnetic field by taking into account the Zeeman coupling, the Zeeman field and the quadrupole nonlinearity. And the main result that I will show here is that when you then control this system as if it's a large angular momentum spin, you can do universal control in order of d physical pulses. And if you're interested, this is published on the archive in this notation. And I will also point out that similar ideas of using nuclear spins and linear bosonic modes for these type of gates have been published around the same time in groups in Sydney and Cornell. So how do we think about large angular momentum encodings? I like to make the analogy to quantum harmonic oscillators quickly, where the operators are given by either x and p or a dagger and a, and you can displace a quantum harmonic oscillator by exponentiating alpha a dagger minus alpha star a, and what you get is a displaced coherent state. So you displace the vacuum to get a coherent state that you can represent using the Wigner function on this infinite dimensional state space. And if you were to prepare Fock state 0 and 1, this is how the Wigner states look like. A large angular momentum spin J has operators Jx, Jy, Jz, or raising and lowering operators J plus and J minus. And you can define a spin displacement in a similar way by exponentiating some complex combination of J plus and J minus. If you reduce this to J is 1/2, you get your spin half particle system back. And then you can get these displacement is equivalent to SU2 operations on the Bloch sphere. So that's your general qubit rotations that you're maybe familiar with. But if you take J higher, you get a larger dimensional Hilbert space. And you can still think of this as a complex phase space. And you can also make Wigner functions defined by this operation here. And then, well, in principle, this could be infinite dimensional because you can parameterize this in angles theta and phi that correspond to the large angular momentum spin rotations as defined here. But then rather than plotting this in spherical coordinates on a sphere as is common, you can map this using a polar projection where the North Pole and South Pole are projected to the center and the boundary of phase space here. And in this case, you have a finite dimensional phase space that looks a lot like the infinite dimensional phase space, but it is a phase space of large angular momentum spin. So we can implement these displacements by picking drives that are selectively picking out every transition. And then by tuning the amplitude of these drives, they can individually, under the rotating wave approximation, effectively realize these off diagonals that are needed to create the spin displacement operator. Here I give what the spin displacement Jy and look for ds3 and ds5. And if you prepare the system in the ground state, drive these transitions, and tune the amplitude of these transitions to match the matrix elements, you get these spin displacement oscillations that coherently oscillate between 0 and d minus 1, back and forward. And you can see that in the middle, you get a coherent, spin coherent superposition between all of these levels. If you were then to measure these and plot the expectation value of spin Jz, you get sinusoidal oscillations between the spin quantum numbers. And so you can think of this as an SU2 oscillation on a large angular momentum spin sphere. So then we can map out the Wigner tomography states that I showed in the beginning. We've already developed all the tools needed to do this. We've shown how to do a displacement operation. We've shown how to do a measurement. And then we can prepare in our lab the 0, the 1, the 2, the 3, the 4 state. We can displace it for different values of theta and phi and reconstruct these beautiful Wigner functions that really visualize the state of any d-dimensional effective spin, large angular momentum spin. We can also use the spin displacement to get universal control. We need to add to that a non-SU2 gate, which in our case, we use a snap gate, which essentially updates the phases of every drive to get a diagonal gate that when combined with our spin displacement gate can be shown to be universal. If you're interested in this, we also showed that the number of physical pulses that are needed, at least from our simulations, then scales as order of d rather than d squared, where d is the dimension of the system, which is the efficiency gain that we were looking for here. We then characterize the performance of these gates by encoding a logical qubit in a spin ket state, and then do logical spin ket operations on this system and measure as a function of random randomly selected number of Clifford gates. We can map out how well we can do as a function of dimension, and that allows us to extract the pulse fidelity here, finding randomized benchmarking fidelities on the order of 99 for DS3 and 98 up to DS8, with pulse lengths of between 50 and 140 nanoseconds. We really understand the errors in the system very well. So this is showing for the DS8 case what happens if we, to the randomized benchmarking, to the infidelity, if we change the gate length here. What we see is that for a very short gate length, these errors are consistent with coherent errors, meaning that if we drive too fast, every individual pulse that is supposed to only address one transition starts to also drive off recently as neighboring transitions, and that leads to coherent errors that would scale as 1 over T2 squared. And then in the limit of very long pulses, this off-resonant driving doesn't become a problem anymore, but the gates become really long. And so we become limited by decoherence. And we came up with a simplified model to fit this, and the predictions match very well. If we then take this model and we predict what we think we can do with these kind of gates using the state of the art with higher coherence times, we believe that we could get an infidelity below 99%, a fidelity above 99% fidelity, even for the DS8 case. And the DS3 case should be able to go above 99.9% fidelity, with still room to win there if we could come up with a better way of pulse shaping our pulses in this coherent error limit. So we have shown that we can read out and control these systems, and we have ideas of how to do this even more efficiently. To conclude, I will talk about the things that go wrong if you go to these higher excited states, in particular thinking about the noise. So you can think of this particular experiment here where you prepare the highest excited state, in this case 10, and then as a function of time, you just measure how the populations decay. And what you will see is that they will really decay from one level n to n minus 1. In principle, you could fit this with some set of rate equations. In principle, we just prepare every nth excited state and measure the exponential decay curve here to fit a number of decay rates here. And then if we plot those decay rates as a function of initial state, what we see is that the first excited state decays has a longer decay rate than the initial, than the higher excited states. We can also measure the dephasing, and you can see that the dephasing time, the Ramsey and the echo, is not quite limited by the 2T1 limit, but it's close to it. If you're interested, these numbers are in the papers that I referenced towards the end. For this talk, I want to talk a little bit about understanding how this decoherence as a function of excited state scales. If you think about the problem of energy relaxation, you need to take into account Fermi's golden rule that essentially looks at the matrix element between the two transitions and the spectral density at that frequency. So if we just consider the matrix elements, you would expect to get some kind of bosonic enhancement that should scale linearly with excitation number. And if you would map that out for the bosonic operators, this would be a linear scaling. And for the Transmon, you would get this deviation from linear scaling. And our data kind of falls in between. I think that we are slowly running out of time, so I will just skip to the end conclusion of this talk, which is that it's not just the matrix elements, but it's also the spectral density that you need to take into account. The spectral density has many complicated microscopic mechanisms that come into play, and we can model them, try to see which one map our data best. And in our case, we think that our measurements are most consistent with saying that they come from dielectric loss. So in summary, what we have talked about is the ability to control many excited states and how to think about reading them out and controlling them using tricks of AMO and large angular momentum spins. We think we have a good understanding of our noise. And then looking ahead, we have now shown that we have promising results for individual qubits. We are really encouraged by the theory of promising things that one can do when now starts to couple these together. So all of these we are exploring in our lab, looking for resource-efficient quantum information processing, analog quantum simulation, and studying transmon physics. And so with that, I would like to point out our team that has worked on all of these experiments, and finally maybe advertise that towards the summer of 2025, we have a conference on coherence in quantum science. So if you're interested, please either check out our website or contact me. And I thank you for your attention, and I'm happy to answer any questions.
Really, thank you, Dr. Block, for your time and super cool and awesome lecture. And we will, if you could answer some questions, would appreciate it. There is a question from our attendee. Can we minimize the circuit depth if we go beyond the binary encoding bosonic QEC, where the complexity increases beyond the binary level? How do you deal with the idle qubits in here?
So we are talking about the multi-qubit algorithm, I'm assuming. And then the question is, what happens to the idling qubits? I think the answer is the same as you would for idling qubits. Idling qubits or qubits will undergo decoherence. And so that's either something that will cause errors on the identity operation, or that's something that you want to mitigate as much as possible. One way to do that is to increase the T1, right? And there's one particular method that works well for qubits that I think could be extended to qubits, which is that low frequency noise is something that affects what we call T2 star, like Ramsey measurements, and that can be decoupled by an Hahn echo. And in quantum computing algorithms using qubits, what you can do is you can just bipulse a idling qubit, and then you get rid of this effect of low, slowly fluctuating noise. And it turns out that you can do the same thing for qubits. So there exists this idea of a qubit echo. And so that would be one way to make the idling error a little bit less. I hope this answers the question.
Yeah. Thank you. Moving to the next question. Why is EJ on EC ratio inversely proportional to charge dispersion? Why must the ratio be of very large value? Could you please elaborate on this?
There is the mathematical answer, which is you just have to solve the Hamiltonian and then find how the Hamiltonian eigenstates correspond to charge noise, and then this is what you find. So that's a somewhat disappointing answer, I would say. This is a result that you get if you quantize the circuit and see how it happens. Maybe intuitively, I do think you could think about if you do the opposite, if you make EC, if you make this really low, effectively what you get is you get a Cooper pair box. So you get this encoding that I showed in the beginning, which is just encoding your states into the charge. And I think it's intuitive to say that if your encoding is heavily favoring the charge encoding, that then you're sensitive to charge noise. I think that's the intuition behind it. Yeah, and then why that's the case for
Yeah.
the excited states, I will admit that when it comes to the excited states, I do lose my intuition for the microscopics there, and then I just do the math, and you see that that's the case. Yeah.
Yeah. Thank you. Moving to the next question. In terms of design considerations, apart from EJ to EC, what are the other things to consider while building qubits, in your opinion?
Yeah, so that's an excellent question. A question that we are actively thinking about ourselves. I will say that this is my excuse to advertise the one slide that I didn't get to talk about in the interest of time. This fundamental trade-off of anharmonicity and charge dispersion, right? So wanting a low charge dispersion, but then therefore needing to sacrifice the anharmonicity. That is something that I think is a design question that you could solve with a better circuit. And this is just advertising work by my student, Mi Rengi Medahine, who worked on these high impedance spiral resonators that could in principle allow you to make inductively shunted transponds that have this additional component of a large inductor, and those do not face the same trade-off. And so this was shown in one group, and we are looking to replicate these and then to find a better trade-off in that sense. So that's one case in which we want to improve. And if you want to learn about making high impedance resonators, you can look up this paper that Mihi published. A second thing that is important, I think, and a big challenge is how do you what kind of coupling do you engineer? So when you do entangling gates between qubits, you need to think about how all of these levels interact with each other. And engineering a coupling that is convenient for the gates that you want to do or the quantum simulation that you want to do, I would say is somewhat of an open problem. There are studies how to do this for Q-trits and Q-quartz already by various groups. And I think that that's an important design consideration that is kind of open. So yeah.
Thank you for your answer. Moving to the next question. Speaking from technological and engineering aspect, would a fully operational quantum computer based on non-binary quantum information require much more of novel design when compared to the existing quantum computers based on superconducting qubits?
Yeah. So that's an excellent question, and I would say a hard no. The reason being that if I just flash a picture of the chip, is that I would say that the beauty is in the simplicity here. If you just look at the design of this qubit chip, it really looks very similar to a qubit chip. So this is an example of EJ over EC qubits going from on the top left, EJ over EC of about 70 down to about 300. And literally that's the only change. So on the top left, you see the type of transmon that Google has, that IBM has, that every lab that does qubit quantum computing has. And as you see, the only physical change that you need to make is you just make your qubit slightly bigger. Now, will that change some of the engineering challenges practically? Of course, you need to rerun your simulation, but does it change it fundamentally? Absolutely not, right? The top left looks exactly the same as the bottom right, up to a small scaling factor. And to me, that's the advantage. As I said, problems like frequency crowding do become more difficult. The readout problem is something that needs to be solved. But I think what we showed in this experiment is that with almost the same tools, you can really squeeze a lot with a small design change out of your system. And I think that that's the power, because it means that all of the hard work into improving the materials and the designs and the boxing and like the filtering, many of those design improvements are going to carry over to qubits. And so I think of it as the opposite. Everything that is going to work for qubit processors, almost everything is going to work for these qubit processors. The only caveat being the control being more broadband. So you do need to improve the bandwidth of your control and your readouts a little bit. So you need to frequency multiplex a little bit more. And that is a challenge that I think is solvable, but that is like the additional requirement that you need. You need to make more broadband pulses and more broadband readout. But from an RF engineering point of view, I don't think that is something that cannot be overcome. And I think a really interesting question then is, is that worth it? Like, does the benefit of the qubit outweigh the downsides? I think on the engineering side, no. Like, I don't doubt that on the engineering side we can overcome these problems. There are interesting open questions on like the compilation side and like how do you deal with noise, and that's more a theoretical qubit question that is to be seen. But in terms of the practical considerations, I'm really not too worried. I'm very optimistic because it's so close to a qubit processor.
Really, thank you for your comprehensive answer. Moving to the next question. How would transmon and fluxonium qubits differ from each other?
Yeah, so that's an
Could you
excellent
please
question.
answer this? Yeah.
And the circuit that I showed in when I flashed this idea of having an IST, an inductively shunted transmon, that is actually the same circuit as the fluxonium. It's just a slightly different parameter regime. So the main difference, I would say, between the transmon and the fluxonium is that the transmon does not have a closed flux loop, whereas the fluxonium does. And so if you now find the parameters of this fluxonium-like circuit, or in our case, we think that the IST, the inductively shunted transmon, which is the same circuit but a different parameter regime, would be maybe even more beneficial. If you look at that circuit, like one worry is that potentially you're more sensitive to flux noise, but really that is one of the design questions that we're trying to answer, like specifically for qubits, right? I would say that the fluxonium has been very successful for encoding qubits, but that was using different transitions than what we're thinking about for the qubits. And so we would really have to sit down and work out all the advantages and disadvantages, look at how the noise scales, look at how you control it. I would say, honestly, we are hopeful that something can be won, and that would be specifically the nonlinearity being, so the circuit in principle allows you to have low charge dispersion and high anomicity. So you get rid of one problem for the transmon. But then we have to sit down and think how the noise scales and how you control it to see if it's actually beneficial. So stay tuned.
Really appreciated your time and your comprehensive and thorough answers to all the students' questions. Dr. Block from University of Rochester, thanks for tuning in and your lecture. Thank you.
Thank you. It was a pleasure.
So this was all for today. We were happy to have you here. It was Marl, your moderator today. And thanks for joining in, and hope you to see you on the next session.